This webcast works on Worksheet 3D, where we're preparing a graphic organizer for representations of accelerated motion. And it's organized in a way that looks at each type of kinematic graph separately. So first, we're looking at position versus time graphs. Okay, so in this table, the left-hand column tells us what do we look for in a position versus time graph. The middle column shows a picture of what that might look like, and the far right column explains what it means. It tells you how to interpret that. So the first thing that we're looking for in a position versus time graph is the graph increasing or decreasing? And so I'll draw a few ways for how it might look if it's increasing. So one example is it might look linear with a positive slope. That line is a it's a line with a positive slope, so it's an increasing graph. But it could also be curved. It could be parabolic, and it could be parabolic in a way that has the slope increasing, which means that the speed is increasing, or it could be parabolic in a way that shows the speed decreasing. So any of these three examples are increasing graphs where the object is moving in the positive direction. By the way, I am drawing my graphs so that they cross the x-axis, because the position of these graphs makes no difference to how you interpret it. As long as the graph is increasing in some way, whether it's linear or curved, you know that the object is moving in the positive direction. Okay, and then it could also be decreasing, and you probably now can guess what these would look like. They might, well, that's not a very good line. It might be linear with a negative slope, or it might be curved in a way that shows the slope getting steeper, so it's speeding up in the negative direction, or it could be curved in a way that shows it getting slower in the negative direction. But all three of these types of graphs are showing something that, basically has a negative slope, and that means motion is in the negative direction. The next feature of a position versus time graph that we might look at or look for are locations where the tangent line would be horizontal. Remember, the tangent line gives us, or maybe I should say the slope of the tangent line equals the instantaneous velocity. At that point in time, where the tangent line is touching our graph, it's showing us what the instantaneous velocity is at that time. Okay, and so there are a few places where we might see a tangent line being horizontal. What if we had something that was first moving in the positive direction but slowing down, and then it changes directions and speeds up as it goes in the negative direction? At the top of this hump, if you will, we have a horizontal tangent line. And so at that point, the velocity is 0. Another example might be, what if it is moving in the negative direction and coming to a stop, and then it speeds up in the positive direction? So again, at the top, or I guess, bottom, of a hump, either one, we would have tangent lines that are horizontal, and they're telling us that for an instant, the velocity is 0. not necessarily the acceleration, right? Acceleration in both of these is constant, but the velocity is 0. There might be one other place where you would see this. For example, if it's slowing down as it's going in the negative direction and then it speeds up again in the negative direction. At this point, the tangent line is 0. Okay. We might also look for locations where the graph is horizontal. So if a position versus time graph is horizontal, and it could be any kind of value, it could be positive, it could be 0, it could be negative. But when the position is not changing, the object is not moving. It's at rest. It doesn't matter what the position is. I mean, it could be at 2 meters. It could be at negative 400 meters. The specific position does not matter. But if you see that position versus time is horizontal, the object is not moving. Okay? Then, for position versus time graphs, we could look for locations where the slope is becoming more steep. And so there are a couple of ways that this could happen. One would be it's moving in the positive direction and getting faster. So it would be curved in this kind of fashion, where at the beginning, the tangential line would be horizontal, but as time goes on, the tangential line would have a steeper and steeper slope. This is telling us that this object is speeding up as it moves in the positive direction. Another type of parabola or curved graph where the slope is becoming more steep would be something like this, where the object is moving in the negative direction. It started out at a velocity of about 0, so it started from rest, but as it goes on, the slope becomes steeper and steeper. Even though the slope is negative, it's becoming more and more steeply negative. So this kind of shape is showing us an object that is speeding up as it moves in the negative direction. Okay? Then we could look for locations where the slope of the position versus time graph is becoming less steep. And so these will also be curved, right, because the slope is changing. But one example might be like this, where the object is slowing down as it moves in the positive direction, or it could be like this, where it is slowing down as it moves in the negative direction. Okay. So we have now shown good examples of all of the things you might look for in a position versus time graph. Now let's look at velocity versus time graphs. Always be very clear what type of graph you're looking at. Okay, so for velocity versus time graphs, where the graph is horizontal and equal to 0. So in other words, oh my goodness, my axes are turned over. Should be velocity in meters per second. But anyway, if the velocity is a horizontal line so that it's staying at the value of 0, that means the object's at rest. What about if the graph is horizontal but it's not equal to 0? And it could be either a positive value, which means moving in the positive direction, or it could be a negative value, which would be moving in the negative direction. But as long as the velocity versus time graph is horizontal, you know that the velocity is constant, so the speed is not changing. And these two are kind of related. Whether the sign of the velocity is positive or negative, the sign of the velocity tells you the direction of motion. So if the sign is positive, and it might be at some constant value, or it might be speeding up, or it might be slowing down. But as long as the velocity is positive, you know that the object is moving in the positive direction. If the sign of the velocity is negative, so it's below zero, and it could be a constant value, it could be slowing down, it could be speeding up. But as long as the velocity is negative, then you know that the motion is in the negative direction. When the graph passes through zero, then the object is reversing direction. So it could start moving in the positive direction and slow down, and then as it passes through zero, it turns around and starts moving in the negative direction. So this point is where direction changes, right? For the first part of this trip, it was moving in the positive direction because the velocity was positive, but it's getting slower and slower. The velocity is coming closer and closer to zero. At this red dot, it changes direction, and now the velocity becomes negative, which means it has turned around and it's moving now in the negative direction. And by the way, that would happen over here as well. Let's say that when we first see it, it's moving in the negative direction but slowing down. And then as it passes through zero, it turns around and it starts moving in the positive direction. So either one of these types of shapes, at the point where the velocity crossed through zero, that is where it changed direction. And then the slope of the velocity versus time graph identifies the acceleration. So, whether acceleration is positive or negative. And so you could have something that is speeding up in the positive direction. That acceleration would be positive. You could also have something that is slowing down in the negative direction, and that acceleration is also positive. And if you see that the velocity versus time graph has a negative slope, which might be a situation where it is slowing down in the positive direction or speeding up in the negative direction, in those places acceleration is pointing in the negative direction. I think I will put a couple of notes here because this sometimes is confusing. This is speeding up in the positive direction. This one, it looks kind of the same except that it's under the x-axis. This is slowing down in the negative direction. I know it's moving in the negative direction because the velocity has a negative sign, and it's slowing down because the value of the velocity is getting closer to zero. Okay. Let's look at acceleration versus time graphs. And all of the acceleration versus time graphs that we are using, the acceleration versus time graph is shaped like a horizontal line. And that's because we are limiting our discussion to situations where acceleration is uniform or constant. That in the real world, acceleration can change, of course, but we are looking at situations where acceleration is constant. And so if you have a value of acceleration that is positive, and it'll look like a horizontal line, but at some positive value, well, that tells you that the velocity is increasing, okay? And if you have a value of acceleration that is negative, that means that the velocity is decreasing.